Hello and welcome to my tutorial on structural and skeletal formulae. Now, structural formulae is a way of writing down an organic compound without actually drawing this picture out. This is called a displayed formulae. Now, most exam questions usually write it out as displayed because they want to save paper. But display formula does have its drawbacks, as if you look here, this is hexanoic acid, and its structural formula takes up a lot of room. You can simplify it to make CH3 CH2 6 times COOH, as like CH2 groups are in the carbon chain along there. So that's one way of writing it, but skeletal formulae is a more streamlined way of drawing it. So if we draw hexane, for example, we just draw the carbon atoms, no hydrogen atoms or any other. Sorry, no hydrogen atoms, but it has the functional groups. So if this was hexanol, then you just simply stick an OH bond on the end. So I've now turned that into hexanol, but those are the only things that are displayed in skeletal formulae. The carbon backbone of the molecule, any branches that look like this, or this, or sometimes even this, and any functional groups as well. So I've just drawn a very confusing branch chain. The way to work out whether you've done a skeletal formulae correctly is to literally count carbons from 1 to 6. So knowing hex means 6. 1, 2, 3, 4, 5, 6, like that. And benzene's skeletal formula looks like this, and what it actually looks like is this, where this is a carbon atom, there's a double bond there to that carbon, but it keeps rotating. You'll find more about this in A2, but for now just appreciate that there are double bonds all over the ring for now. So we'll now move on to the next part, skeletal formulae and functional groups. So in order to represent a double bond, you draw a bold line next to your carbon to carbon chain in order to represent a double bond. So this one is shown between carbon 2 and carbon 3. So two parallel lines are used, and when you have a functional group like this, so I'll just draw it out, have OH here, this is butan 2O, but meaning 4 carbons, and there's an OH group on the second one. So we have 1, 2, 3, 4, and this is the skeletal formula for pentanoic acid. Hexanoic like we had in the previous example, would have another carbon chain. Another carbon bond there, but we could count the carbons again. 1, 2, 3, 4. Now on carbon 5 we have our double bond oxygen and our single bond OH group. So that's how to represent a carboxylic acid on a skeletal formulae. And if we just look at more complex structures now using JMOL, so I'm going to look at paracetamol. So now it's loaded paracetamol. So it has a that there is a nitro group. This is the double bond oxygen here, CH3 group here, and the hydrogen atoms are here. One way to represent this as a skeletal formulae is to draw your cyclohexene ring first, like this. And we have a 1 double bond, 2 double bond, 3 double bond, and an OH here. And a nitro here. And then a double bond oxygen for the ketone now. Once I rub out this so I can make some more space. This is the ketone now. We draw an OH here. I'll just rub out this. So this is what the paracetamol would look like, turning this into this. So it simplifies very complex structures very quickly and easily. So that's why skeletal formulae is needed. However, you do not need to learn such complex structures like paracetamol, but it's nice to appreciate that complex compounds can be dealt with very quickly and easily. So if we go back now to 2.1.7, where we go on to talk about isomerism. Now, this is the idea that when molecules are composed of the same number and types of atoms, but they're arranged in different ways of space. So if we look at propanol now, so propanol, we know, so it has 3 carbon atoms and an OH bond on the end, saturated with hydrogen atoms. But another way to represent this is propan-2-ol, where the OH group moves from carbon 1 to carbon 2. So this is exactly the same empirical formula, C3H8O, or if you prefer the other way, like I showed you in the previous tutorial, it would be C3H7OH. But this is the more this is the more revered way of representing it. So that's what it looks like. So there are different arrangements in space really, but they all have the same empirical formulae. So I'll just type out the definition now. So moving on now to EZ isomerism. So a molecule must satisfy 2 criteria to have EZ isomerism. A carbon-carbon double bond must be present, and each carbon in the double bond must be attached to 2 different groups. The compound ClCH double bond CHCl has a special case of EZ isomerism. There is a chlorine atom on each of the carbon-carbon double bonds, and if the positions differ. So a trans isomer, the groups are on opposite sides, and a cis isomer groups on the same side. Now this happens completely randomly, but the knowledge that these both presents are very key. So skeletal formula can also be used to represent EZ and cis trans isomers, and the cis trans isomers of butene are shown below. So we'll have a look. And the butene is represented like this, and the butene on this side same side, different side. Trans, different opposite sides. Cis, same side. So we'll move on now to organic reagents and their reactants. So homoelectric fission is the breaking of a covalent bond with one of the bonded electrons going to each atom, forming two radicals. The two species are of the same type, homo meaning the same. A radical is a species with an unpaired electron, so a radical is a covalent bond taking one of the shared pair of electrons with and this said electron is unpaired, so we use a dot to represent that unpaired electron for that atom. And heteroelectric fission is the breaking of a covalent bond with both of the bonded electrons going to one of the atoms, forming a cation, which is positive, and an anion, which is negative. Hetero is different in this case. So X is covalently bonded to Y, forming two ions, oppositely charged. And a nucleophile is a reactant that attacks an electron deficient carbon atom, i.e. it doesn't have enough electrons, so it donates an electron pair in order to satisfy that carbon atom. Nucleophiles are often negative ions with a lone pair of electrons. Nucleophiles often include an electronegative atom with a lone pair of electrons and a delta minus partial charge, which is why water is there. If you look back at my previous tutorials, then you should know that oxygen has two lone pairs, but in this example they've only shown the one lone pair, as that's all that's needed in order to interact with the carbon atoms in such a way. And an electrophile is a reactant that attacks an area of high electron density, accepting an electron pair, and they're positive ions, so some molecules can act as electrophiles and they have a delta plus partial charge. So moving on now to addition reactions, and this is when two reactants combine together to make one product, and a molecule is added across the double bond of an unsaturated molecule to make a saturated molecule. So we'll look here at the addition reaction. So if we have ethene plus bromine, it will make 1,2-dibromoethane. So both the bromine atoms are added on to the ethene molecule, breaking the double bond. We'll find out more about how this happens in a bit. And this is the substitution reaction for bromoethane plus a hydroxide ion, which is a nucleophile, and this makes ethanol and a bromide ion. And this is an elimination reaction where one reactant reacts to form two products. A molecule is removed from a saturated molecule to make an unsaturated molecule. So we'll just have a look. Now where it says acid catalysts, you should be thinking in your head that acids are a source of H plus ions. So if you get stuck, you could always write H plus ions. And then ethene plus water is what is made. So basically it reverts, with the exception of the creation of a water molecule. So now we'll look at the key definitions. A substitution reaction is a reaction in which an atom or group of atoms is replaced with a different atom or group of atoms. In a substitution reaction, two reactants make two products, and in an elimination reaction, it refers to the removal of a molecule from a saturated molecule to make an unsaturated molecule. One reactant makes two products. So we move on to the next page. We'll look at hydrocarbons from crude oil. So I recommend you get the textbook and have a read through this particular page. So fractional distillation is the separation of the components in a liquid mixture into fractions which differ from in the boiling point by means of distillation, typically using a fractioning column, which is this massive thing here. So inside the column we have different places where the temperatures are different. So if you have petroleum gas at 20 degrees, this is where the shorter chains are here. So yeah, longer chains are here, shorter chains are up there with petroleum gas. So The effect of chain length. As chain length increases, the boiling point increases because the intermolecular forces, or van der Waals forces, between the molecules get stronger. In a longer chained alkane, there are more points of contact between the molecules, leading to more van der Waals forces between the molecules. It takes more energy, so therefore a higher temperature is needed to separate the molecules. This allows the different alkanes in crude oil to be separated by their boiling points. So this is a quick picture of it. So we have increased chain length means more van der Waals forces between the molecules, so you get a higher boiling point. So increased branching means the molecules have fewer points of contact and they're further apart than non-branched molecules, so there are fewer intermolecular forces. So branched chains boil more easily than increased chain length. So now we'll look at hydrocarbons as fuels. So if we look at the combustion of alkanes, so whenever you combust something, you need to have an excess of oxygen. So this always forms carbon dioxide and an amount of water. So if we take C8H18, which is octane, plus 12.5 lots of oxygen, we have 8 carbon dioxide molecules being made plus 9 H2O. This is what's known as complete combustion. Now if I didn't have so much oxygen, like in a car engine, I would use the same amount of fuel, but if I didn't have so much oxygen, I would get carbon monoxide and 9 H2O. Now everyone knows that carbon monoxide is really poisonous and it makes people very ill. Not good. So catalytic converters remove the carbon monoxide and allow it to bond to another oxygen and to form either nitrogen oxide or just CO2, which is less harmful than carbon monoxide to humans, but we'll find out more about that as we get into green chemistry, which is right at the end of this unit. So we'll move on now to the next part of this. Cracking. Now cracking is the separation of the really long chains of hydrocarbons into shorter chains. So we have one shorter chain here and the slightly shorter chain than before. So it's the breaking down of long chain saturated hydrocarbons to form a mixture of shorter chain hydrocarbons. So dodecane, which is C12H26, can form C10H22 or decane plus C2H4 or ethene. So a branched chain can form this, and it can also form a cyclic hydrocarbon as well, like cyclohexane plus hydrogen, or 2,2-dimethylpropane, which is a branched hydrocarbon. So if we go back to the textbook, so this is pentane, makes cyclopentane plus H2, and we'll look at incomplete combustion. So this is the example I had up on the board, and this is why carbon monoxide is dangerous. I'll give you pause the video, can have a little read about it. And this is fossil fuels and fuels of the future. So this is a little bit of politics and how biofuels are needed to replace fossil fuels, and how the global warming is affecting it as well. So I'll go through each paragraph in turn, give you a 5-second pause, and you can have a read through it. There's not really much chemistry here, it's more political, but I won't say too much, or as YouTube might take off the video. So that's one. This is a flowchart of LPG, kerosene, residual fuel, and bitumen, and how people use it every day. Mostly it's in petrol and diesel and heating oil. So the use of crude oil from fuels. This is a smog, which is the deadly gas of carbon monoxide, and it's very poisonous. So people probably wear gas masks in order to get most of the carbon monoxide out of their lungs. This is global warming and climate change. A glacier is being melted due to increased levels of UV radiation and infrared radiation, but we'll find out more about that in the green chemistry section. This is a cartoon, and this one quite funny when I first looked at it, but it's got quite a serious message. So if we zoom out, to the future, and that's it for this tutorial. I hope you found this useful, and I'll see you next time when I talk about substitution reactions of alkanes and the different reaction mechanisms that are needed. When we talked about the substitution reactions and the elimination reactions, I will talk more about them. But thank you for watching, and see you next time.